So as we go through our goals today is to organize qualitative data in tables, construct bar graphs, construct pie charts is what we're going to go through today. The notes may take me about 30 minutes to kind of go through, 40 minutes, and then I pulled in a bunch of other problems for us to practice together. Turn you loose, let you do one, we get to check it and so forth. And then we should have some extra time to get into your homework and keep chipping it away. Again, we're going to use that time wisely. As we do things, eventually the math will take longer, and then, lectures will go a little bit longer. So a frequency distribution, we have two types of frequency distributions we're going to see here in a minute. We have one frequency distribution that's based off of counts, and another one that's called a relative frequency distribution, which is based off of percentages. Okay, so the first one here, they have a set of data here on the last side here, and they asked us to create a frequency table using like your tally marks to come up with, well, how many, when we look at the body parts for, we have back, wrist, elbow for pain and so forth. And so we just need to kind of quickly go through, give you about 30 seconds to a minute to start putting little tally marks in there. Like I see back in there once, so I'm going to put, a little slash on there. So back I see once. Oops, my pen's not working. And back is once. We see wrist once. We see elbow. We see back again. So as you go through, let you finish that out real quick here and create that little frequency table. Do it, you can do the tally marks, and then eventually once you get done with tallying them all up, then find the sum of each of the different categories there for wrist, back, elbow, hip, and such and such. So again, I'll give you a chance to work ahead of me and kind of create that. Some of these I already have done for us just because it'd be so labor intensive. This is a good one to kind of get warmed up. And when you get done, you can take a peek up at the screen, see if you got the same number I did. Of course, it'd be good if Mr. Stevens can, look at his notes and write in the same columns at the right time. That was off a little bit there. So here we've created a kind of a frequency table is what we've created. And again, from here, as you continue doing what you're doing, from here we have several different options for displaying the data. We can put it in a bar chart if we want to. We could do a dot plot is something that we can do. That's more of one of tomorrow's lessons, but we could do a dot plot of it. We just got to make sure that as we do, I wouldn't do a histogram because histograms are, thank you, Ollie, histograms are typically associated with intervals of data. But a bar chart would be appropriate for us to do. I have all my calculators over there. So now we're going to go down here further. We will create a bar chart, or I may already have one created for you. The next thing we're going to do is we're going to talk about a relative frequency. A relative frequency table is basically based off of proportions or a percentage. It's the percent of observations within a category and found using a formula. So when we're looking at the relative frequency, we look at what is the frequency of that one thing occurring, and then we divide by the total of all of the occurrences in that topic. And so as we create our little relative frequency table down below, there is a total of 30 in our sample here. So as I go to find each of these relative frequencies as a percentage, I need to carefully go through and say, okay, what is 12 divided by 30? Get that as a decimal. What is 2 divided by 30? And again, as we do these, and as you go through, and if you want to divide them out real quick, you can. Take them out to 4 decimals is what we're going to do, is take them all the way out to 4 decimals. Then we do 1 divided by 30, 2 divided by 30. And we have several repeats here, so some of these we just have to do once, and then we can copy that decimal down again. But this gives me my relative frequency, is what it gives us. Eventually later, we'll talk about a cumulative relative frequency, and what does that table look like? How is that displayed? It's going to look a little bit different from what we're doing right now, but this is just your general relative frequency table. And the reason why we're going out to like 4 decimals, it kind of keeps us more accurate to where it all adds up to maybe 1 exactly, or just a smidge under 1, like 0.9999. Okay. Sometimes when we go to the first decimal or the second decimal and we're rounding or truncating, the sum of what we're doing doesn't add up to be 100%. Taking it out more decimal places kind of keeps us more on the accuracy aspect, and we stay closer to that 100% or 1 as we look at adding up all the little proportions. So here's our little relative frequency table. And again, we're going to practice doing this later on, more by hand of the whole process, unless you draw the graphs. But the key thing is knowing the difference between a frequency table means I'm dealing with counts. A relative frequency table means I'm dealing with proportions. I'm dealing with percentages. And that's a big deal when we go to display our data. Does anybody need what's up on the screen a little bit longer? I don't want to rush you too quick. So a bar graph is constructed by labeling each category of data on either the horizontal or vertical axis. So we can do a horizontal bar graph. Typically, most of the time, I think a lot of us use the vertical bar graphs where the bars are going up, but you can do, with this type of information, we can do a horizontal bar graph. I have some in our lesson today. When we get to histograms, we're doing a vertical histogram is what we're doing. So sometimes it's just easier to stay with one pattern of doing it vertical. That way, but we do see sometimes, and we talk about it in here, why sometimes do we do a horizontal in there. We got to make sure as we draw this that rectangles are the same width as we go through the process. And then, as we label it, we need to make sure that, and you should be able to, I think, if you touch home and then click on the picture, you can make that picture larger. If you click on home, then use your finger, you can drag and make that thing wider if you need to make it wider to be able to look at it. But I went ahead and kind of put the pictures of this in there for you for the first example, just to show you what a frequency table on the left side looks like as a bar graph. What does a relative frequency table look like on the right side? On the frequency table, when we're scaling, we got to make sure we use a consistent scale. We got to make sure we start at 0 at the bottom. We have all the widths of the rectangles are the same width. And we don't have to go up forever. We can go up to the highest number of frequency. That could be our top out for the vertical scaling. On the relative frequency, it's percentages. So we want to, go through, find some nice common, either 5%, 10% is what this one is going by. They went through and used the same width for each of the rectangles. We don't have to go up to 100%. Okay. We will, when we do a cumulative relative frequency, we'll actually go up to 100% or 1 if we're labeling as a decimal. The scale on the left-hand side will go all the way up to 100%, but a relative frequency, we can just go up as high as our biggest percentage or proportion is for labeling purposes. Can you go up a little bit more to 0.5? Sure, if you want to. There's nothing wrong with it. You can go up all the way up to 100%. But you don't have to when you're doing the relative. The cumulative relative frequency, it has to, because we're saying, hey, the cumulative adds up to be 100%. So we want to see what that looks like. Again, that'll be another lesson when we get into it. Couple little notes just to be careful, because here are the characteristic questions we always get asked. Hey, what's misleading about this graph or this graph that they have displayed here? So not starting on the left scale at 0. So instead of having a 0 down there in the bottom left, they went through and they said, hey, let me start this first one at like 2 and then 4, 6, 8. That's a way of misrepresenting what's taking place, and it's a misleading thing. And so we want to make sure that we start with with 0 down there, whether it's a relative frequency or if it's a frequency. Make sure they say, hey, what's misleading? Unequal widths, doing different colors, because again, different colors, unless you're colorblind, different colors kind of draw our eyes to certain things. And to me, if I'm using a fluorescent color, that's going to draw my eyes closer to it and focus on that more than another color. And so they want to make sure you're using a consistent color for everything. And now, if you're doing more than one category, more than one thing, like we're breaking each of those things down for back and wrist for males and females. Well, then I'm going to have to do 2 different colors. But make sure all the males are one color and all the females' data is another color. And consistently. And then also when we do 3-dimensional bar graphs, that also is a way to misrepresent what's taking place and mislead people and stuff, because seeing it in a 3D setting, we start looking at the width and so forth of that rectangle, that whole big rectangle 3-dimensionally, and it kind of distorts what's taking place. We don't see these types of charts that often. The Pareto chart, as all the way up into school right now, you have it. Okay, this is just one of those new things in the college math that they kind of introduce it to you. We have what's called a Pareto chart, is a bar graph whose bars are drawn in decreasing order of frequency or relative frequency. Okay, so instead of putting in the way let's say we did it alphabetical on the first one. Here, by using this type of chart method, you're going with the biggest percentage first, and then down to the smallest percentage is what you're doing. Okay. Again, that's a new one that we haven't used before. Side-by-side bar graphs. Data sets should be compared by using relative frequencies when we do that. So using proportions, not counts, is what that's talking about. Because different sample or population size make comparison using frequencies difficult or misleading. I think they have an example down here on the left-hand side, and we're going to go through and fill in the table. But notice how there's not the same number in 1990 and the year 2017. As they look at the number of people that were surveyed or gathered data from. So with that in mind, we don't want to do a frequency chart for the bar chart based off of counts, because we don't have the same total sum. So that's why they're saying, hey, let's convert these to percentages and then do a relative frequency side-by-side bar graph. That way, then we can make some comparisons about the different, whether you got a high school diploma or didn't get a high school diploma or had some college and so forth. So we're going to take a minute and go through and create the proportions for each one of those. So I'll let you go with your calculator. Go out 4 decimals, roughly. Or round to the 4th. Turn each one of those things. I think I have it in order the way it's up there. I tried to be careful on type it in. It looks like, yeah. So go ahead and go through and do the 1990. Turn on create those 12 decimals for me. So give you a chance again to warm up. I do have the graph done for us, just to save us time on this one, but just to, get you a chance to practice doing it. Practice getting the relative frequency stuff. I know when you're not actively doing things, sometimes we tune out. And then as you get close to finishing, you should be maybe done the first row. I got both columns done for you if you want to check, or if you're done doing the division, like, okay, I've had it, I'm good with practicing that skill. I got the rest of those things filled out for you. Any questions on creating that relative frequency table? Try to make sure I get the line doesn't mess you guys up. Now, since, this, as you look down below, if you scroll up, you'll notice it's a horizontal bar chart is the way they decided to graph this one. I gave a little note on why they chose to do this one by a horizontal bar chart. Because the category names were so long, it was just easier, to do it as horizontal to go out the process. Again, notice how they kept the same scale horizontally with 0 and working out. They use two colors that are kind of neutral to where they're not, making your eyes draw to one thing or another. But they made sure for the 2 different years they had 2 different colors. And then now we can start asking some questions about, the proportion, as we phrase it, not count-wise, but the proportion of, obviously when you look at education attained in 1990. There was a higher proportion that did not graduate high school. It also had a higher proportion that did have a high school diploma compared to 2017. We can notice in 2017 there was a lot more bachelor degrees that were earned compared to 1990. Same thing for graduate or professional degrees. There was a greater proportion of those degrees obtained in 2017 compared to the group from 1990. Um, some college, no degree, almost about the same, close to being the same proportion. There's not a big difference there. But we can tell there is a big difference. There is a lower proportion that did not graduate high school in 2017 compared to 1990. Okay. Then we could go through and ask the question, well, why? What caused there to be a lower proportion of not graduating high school in 2017 compared to 1990? Are we doing things educationally better to retain kids, to help them get to not leave school and not graduate without a high school diploma? And that would be some things, you start looking at, okay, what was done differently in those two settings? A pie chart is a circle divided into sectors. Each sector represents a category of data. The area of each sector is proportional to the frequency of the category. Now, this one gets a little bit challenging. Instead of you having to do the whole table here, basically what we'd have to do, and I made a little note here, once we go through and we look at the frequency, we get the relative frequency like we just did in the previous example. When we go to draw the pie graph or the pie chart, we actually need to take each of the different degrees for each of the relative frequencies and multiply it by 360 to figure out what portion of a circle does it get. And that's what we base as we go look at seeing how big of a slice of the pie do each of those category gets. We need to take each of these relative frequencies and multiply it by 360. Whoops, that's a 0.1201 and then times 360. And that gives us roughly 43. So that's what I went ahead and did that for you. Now I have an open circle down below where you get to draw a pie chart, is what you get to go through and do. And personally, if I was doing this by hand, I would start with the 98 degree one, because that's almost a 90 degree. It's a little bit bigger than a 90 degree, right corner. So as I would do it, I would say, okay, if I come down to, there's the center, and I come straight across, I know that's 90, so I need to be a little bit more than 90. And so then I'll go back and get rid of where the 90 part is. And so there's my 98. And then that was for high school diploma. And then I would pick the next category that may be easy to do. The not high school diploma. I'm going to do that one because that's close to being 45%. So if I think about drawing a horizontal line out here to the left, I could maybe just go a smidge in front of 45 degrees, and that looks like it's about 43 degrees. And then I would say, okay, that's going to be my no high school diploma. And then I'm going to erase the little line there. And then now, small chunk, let's see. What do I want to do next? Oh, graduate and professional. That's another one that looks like that's about 45 degrees is what that one is. So I'm going to go in here and say, all right, let me just go ahead and take this one just a little bit above the horizontal across, and this will be my graduate one. And then now I need to split this next one up into a 71, a 73, and a 31. So now it's just a little bit of estimating. I'm thinking maybe about there. Looks like about a 70. And then maybe here. So I'm thinking these two are my 70. So I'm going to put bachelor in this one. And then I'm going to put, what's my other 70? Some college. And then that puts the associate degrees in that little smaller chunk. And so that's what I would do is if I was going through, once I convert the relative frequency, multiply it by 360 to get the degrees of a circle, then I would just start, working with which one's closest to a right angle. Sketch that in there. And then now, it's kind of, everything looks pretty decent. It doesn't look like I went too crazy on the distortion of what's there. Again, it can be in any order. I just chose to start with that right hand, top right corner for it being about 90 degrees or 98 degrees. Again, we don't use them that often, especially using it for displaying statistical information when you look at educationally. Where do we usually see pie charts pop up more? On TV, when we're looking at the news, watching the different things. Maybe online, looking at newspapers and other little sites there. That's where they have a tendency to do it. They'll do it in books and stuff. They'll use pie charts to represent stuff. But most of the time when we're doing statistical data to display it, a pie chart is not used because it's way too easy to misrepresent what's there. And besides the fact, a lot of time we forget to multiply the frequencies by 360 and find the area of the circle or portion of the circle that it's supposed to be. And then that's when we start getting things being really distorted. So there's our little pie chart. And so now as we go through, we just got some practice ones is what I have. So as I said, this is going to be a quick lesson, not too long. Tomorrow, same thing. It'll be pretty quick, which is nice. That way you can kind of get a head start on homework and get things going. So let me give you a chance and let you read number 5 here. And then I'm going to ask you guys to kind of help me answer it with the A, B, and C. So the USA Today type chart shows the top responses to the question, who the most difficult to sell yourself to? First question is, what was the most common response? And then the survey of 1,053 adults, how many stated their significant other must be difficult to sell yourself to? And then explain why this graphic cannot be displayed in a pie chart. So on A, which one was the most common response? You can holler it out loud. Boss. Yeah, boss. Thank you. Thank you, boss. All right. What about how many stated their significant other is the most difficult to sell yourself to? So we know it's 15%, but it said how many, Jackson? Yeah, how'd you get 158? Oh, very good. So you went through and did 1,053 divided by 100, and then you multiplied it by 15. Okay. All right. Then times 15. What's another way you can do it? Sorry, you did 15, not 0.15. You did 15. What's another way that you could do that one? Yeah, Mason.
1.5 times 1,053.
Sure. Or you could do 0.15 times 1,053. Again, either one of you is going to give you that same thing. Okay, and again, you got to do the one that makes sense to you. All right, I would do the 0.15 times the 1,053 because that's more natural from the way I do things. But if you want to divide the big number by 100 and then it's a normal 15, that's fine too. Okay. Why is it not appropriate to do this one in a pie chart? Doesn't equal 100%. Okay. All right, so the sum does not add up to be 100%. Or sometimes we'll see instead of 100% an option being 1. Okay, because especially if we see them listed as proportions where they're all just straight decimals. So if they gave us like 0.25, 0.20, and 0.15, we don't know what the whole thing is because the sum doesn't add up to be 100. Okay, so that's why we want to stay away from doing a pie chart on this one. They didn't give us an other category. Now, if they gave us another category that said other, and then that was the other amount that actually got us to 100, then we could go about doing a pie chart with it. Okay. Number 7, most valuable player. The following Pareto chart, shows the position played by the MVP in the National League. Which position had the most MVPs? Yeah, outfield. Okay. How many MVPs played first base? Okay. How many MVPs played first base? Then how many more did first base than third base? 5. Yeah, 5. Thank you for hollering that out. I appreciate that. There are 3 outfield positions, left, center, right field. Given this, how might the graph be misleading?
Doesn't show which outfield position have the most MVP.
Yeah. Right now, I grouped them all 3 together. It'd be nice to know did more center fielders, more left fielders. We just don't know for the MVP. That's all grouped together, and so we don't know, which one was the greater. Was it the center fielders had the greater MVP amount of great MVPs, and so forth. So here, we don't know the breakdown for each of the outfield positions. We know collectively as a whole the outfield has the most, but, hey, how does that 30, looks like what, 33, 32, based on where that line is, somewhere there, something like that, around 33 outfielders have won MVP awards. We just don't know. Is it an even split, 11, 11, 11? Or is it greater for one of them? Or is it less frequent for one of the outfield positions to get a MVP award? So, knowing I have several baseball players in here, which one do you think probably in the outfield would be more likely to get the MVP? Which position?
Probably center field.
Probably center field. Why?
Let's get the most balls.
Okay. Most balls going towards center field? Okay. All right. All right. Number 9, divorce. The following graph represents the results of a survey in which a random sample of Americans was asked. Please tell me whether you personally believe that, in general, divorce is morally acceptable or morally wrong. First question. What % of respondents believe divorce is morally acceptable? What does it look like? Just under 70%, so somewhere around 68, 69 if they actually gave you multiple choice. But, so here we're just saying just under 70%. We can probably say maybe approximate. That's one thing statistics like to do, approximately 70%. So we know we're right in that ballpark. But it would be fine to say 69 on there, 69%. We like using a statistic, the word approximate, because it gives us that wiggle room, is what we do. And we're going to see that later on as we talk about things being approximately normal. May not be perfect normal, but they're approximately normal. Now, part B, it says, if there are 240 million adults in America, how many believe that divorce is morally wrong? All right, so how'd you get that?
Multiplied it by 0.23.
All right, so yeah, and I agree with that. That looks like about 23%. It looks like it's about 22 to 23%. So taking 0.23 times the 240 million. Now, did you put in all the zeros?
Yeah.
Yeah, and that's what I would do too. I would put in all the zeros, and now you didn't have to. You could have done 200.23 times 240. You just got to make sure you tag the word million when you get done on the end of that number, is what you got to make sure you do. But yeah, so with that in mind, then we end up getting that answer, about 55, 200,000. So 55,200,000. Part C, if the Gallup poll claimed that the results of the survey indicates the 8% of the adults believe divorce is acceptable in certain situations, would you say this statement is descriptive or inferential? Well, it is inferential. Now, why is it inferential? Well, to me, we don't. We go ahead. Anybody want to say why they think it is? Yes.
Because it's using information from a sample and then applying it to a population.
Okay, very good. I like that. Using the information from a sample, using it and applying it to the population. What else could we say? Anybody want to add to that? I think with it, to be more descriptive, to say prescriptive, we would have to be more concrete in what numbers do we have there as data to look at. And so, so I think, there is, since we're looking at that being roughly about 8%, we're kind of inferring to the greater piece. All right, next one, identity theft. Identity fraud occurs when someone else's personal information is used to open a credit card account, apply for a job, receive benefits, and so on. The following relative frequency bar chart represents the various types of identity theft based on study conducted by the Federal Trade Commission. Approximately what percent of identity theft was loan fraud, which is applying for a loan in somebody else's name? Yeah, I heard that, 5%. That one right there. And then if there were 10 million cases of identity fraud in a recent year, how many were credit card fraud, where someone else uses credit card to make purchases? What, about 2.6 million? 2.6 million. Again, all I did was I said that was roughly about 26%. So 0.26, I times it by, I just did it times 10. So I can just move the decimal over one. This is the last one, and then we get to do a long one together, doing all the parts to it. So Made in America. A sample of 2,163 adults age 18 and over were asked, when you see an ad emphasizing that the product is made in America, are you more likely to buy it, less likely to buy it, or neither more or less likely to buy it? The results of this survey are presented in a side-by-side bar graph below. And they asked us what proportion of 18 to 30-year-olds responded to more likely to buy when made in America. So as we look at that first part, what would be the blue amount there? What do you think? Somewhere around about 43%, something like that, maybe-ish, approximately 43. So for the first part, we'd say somewhere about 43%. What proportion of 35 to 44-year-olds respond that they're more likely to buy America? Just like a smidge over 60%, doesn't it? So we're looking at, for that one, we're looking at just a little bit over 60%, so maybe 61%, approximately 60%. Which age group has the greatest proportion who are more likely to buy when made in America? So which is with a taller graph? It's the category that I'm almost in. The 55 plus, they look like that they have the greatest proportion. Which age group has a majority of respondents who are less likely to buy when made in America? Were you thinking the 18 to 34-year-olds? Which one had the tallest green section? Yep. But eventually we get you, once you guys get to past your 34s, you start thinking about America. What is the apparent association between age and likelihood to a buy? This is where we get to make a comment. As age increases, there is a greater frequency of buying being more likely to buy American-made products. That's one thing we can say. We could say 18 to 34-year-olds have a greater proportion of being less likely to buy American-made. All right, so there's several things you can say in here. you know, when you look at it, you know, you can start comparing the differences between the proportions. You know, there's a greater proportion of, you know, 55 plus that are more likely to buy than less likely to buy. So there's several different correct answers for that interpretation when we're saying, hey, what kind of association do you see inside this bar chart? Okay. If it was presented as a multiple choice question, you're going to make sure you look at it and say, hey, does that make sense for the context of what I'm seeing in the picture? So this one here, give you a chance to kind of work this one out fully, where you're going to construct the relative frequency distribution for males and females, do a side-by-side relative frequency bar graph, and then compare the online shoppings with the habits of males and females. So I'm going to let you do that for the next 10 to 15 minutes. I'll put up eventually what it looks like, and did you have something close to it? As soon as you get it done, get into the homework, but just wanted to give us a chance to work on one of these together is what I want to go through and do. All right, so on the video here, what I have here is I have what the relative frequency table would look like for the males and females right there. And then what would the bar graph look like a side by side? And again, you could have done this one as a horizontal bar graph if you wanted to. And then lastly, for answering the fourth part, females are more likely, this is one of the things you can say. Females are more likely for Instagram to influence their online shopping, while males are more likely to have none of these platforms influence their online shopping.